Okay, good afternoon, everybody. A very warm welcome to all of you. We'll just get started for the meeting with some housekeeping in just a moment. So we're delighted to bring you the November meeting of the 2020-2021 session via a webinar. And it's great that so many of you can join us again for the next instalment of the RAS Ordinary Meetings online. So first, I'm just going to go through some housekeeping for the meeting. So hopefully if you look at the top left of your screen, you should see a small green shield, and that symbol means that you're using the most up-to-date version of Zoom and that it is secure. I do also need to advise you that this meeting is being recorded. Questions can be asked to the speakers at the end of the lecture, but as you will be muted, you can use the chat facility to ask your questions, which is found at the bottom of your screen. And your questions will go only to the panelists for us to see and read out at the end. Now, the questions will be read out by Council Member Dr. Shona Urquhart, so thank you to Shona for helping out with that today. One more thing on the questions, for the purpose of the Observatory magazine report, please could you write your name at the start of your question if you're happy to be included in that. Okay, so let's get going with the ordinary meeting. So first of all, first item to remind you is of some important deadlines, and the first is relating to the elections to council. So can I remind you to propose a colleague or put yourself forward for election to council, and the deadline for nominations is Friday the 27th of November 2020. The second item in terms of deadlines relates to the RAS prizes for the best PhD theses in astronomy and geophysics submitted in 2020. So prizes for the best theses in astronomy and geophysics, astronomy and astrophysics, the Michael Penston Prize, and solar system sciences and geophysics, the Keith Runcorn Prize, are now open for nomination. And the closing date for nominations for both awards, which carry a cash prize of £1,000 each and the opportunity to make a presentation at a future ordinary meeting, is the 31st of January 2021. Okay, fantastic. On to the main programme. So today we're going to have two speakers and we're going to begin promptly with our first speaker, Amaury Triaud from Birmingham University. And Amaury is the Fowler A Award recipient for 2020. So Amaury's talk is going to be about the Ultracool Dwarf and the 7 planets. Over to you, Amaury.
Yeah, thank you very much, Emma. Thanks to everyone for joining us for this meeting and coming to be interested, I hope, in this topic. I'm going to share my screen first here. And hopefully you should see now the slides. So the Ultracool Dwarf and the 7 planets, this is relating to the discovery of the TRAPPIST-1 planetary system. I don't know, a few years ago, I don't know if many of you have heard about it or remember, but effectively the system is just north of the ecliptic in the Aquarius constellation. And around this star, very faint and cold stars, we detected 7 planets that have the size and the mass similar to the Earth. What's particularly interesting is this system is that the distance between the star and the outermost orbit here is about 7% only of an astronomical unit. So imagine it as a very compact planetary system. In fact, it's so compact that the distance between these 2 planets right there is only 3 times the Earth-Moon distance. So the planets are really big in each other's sky. And if you were to sit on this planet on the night side, as it goes into conjunction with this one, you would see it about as twice the area of the full moon in the sky, which would be a pretty spectacular sight, I imagine. What's interesting in the system is not just its beauty and its arrangement, but the fact that the planets are considered temperate, meaning that under certain conditions, certain times very exotic geologic and atmospheric condition, you could expect water in a liquid form to remain for billions of years on at least one part of the surface. It doesn't mean that it is there at the moment, but certainly it opens the possibility to investigate that. And those planets are fast becoming one of the most interesting laboratory to find out about exoatmospheres, the climates of rocky planets outside the solar system, and the search for life elsewhere. So why did we choose to observe such a strange, cold, and small star to begin with? So this star, which is only 10% of the mass and the radius of the sun, is part of the most numerous population of stars in our galaxy. So this is a histogram, a census of the 10 parsec sample around the sun. And most of the action around in a search for Earth analogs happens around here, about 1 solar mass plus or minus 10%. And this only constitutes about 15% of the stellar content in our galaxy. And half of those are binary stars, and they're usually excluded. So really, the search for Earth twins is only considering only 7 to 8% of the stellar content of the galaxy. However, half of the stars in the galaxy are less than a quarter of the mass of the sun. They're right there. And therefore, those are the most common stars. And if they have planets around them, those might be the most common planets out there as well. And we'll see that we have good indication to think that. Another element that is important here is that we want to understand planet formation in a general sense. So looking for the most common planets and the most common stars is important. But what we also want to find out is what is within the atmosphere of the planet, how we can remotely explore an atmosphere without ever leaving the solar system. And the method that we're going to use for that is called transmission spectroscopy. And for that, you have to imagine that you have a star here, you have a planet there, and then you as the observer is on the right-hand side. If the planet passes in front of the star, it transits, then you have a deficit of light, which you can measure. And it comes in relation to the area of the planet or the radius square of the planet compared to the star. If your planet has an atmosphere, and here I've put an atmosphere that scatters bluer wavelengths like Earth does, then those bluer wavelengths will get interrupted by the atmosphere, making it opaque to a remote observer. And you'll measure an apparent size, which is slightly larger than the actual surface of the planet. Redder wavelength, however, goes through the atmosphere. We see that notably during a lunar eclipse. And therefore, one would measure an apparent size that is ever so slightly smaller in the redder wavelengths compared to the blue. And you would deduce your planet is bigger in blue. Therefore, there must be a source of opacity within the atmosphere. And then you can match the sources of opacity to specific molecules, to Rayleigh scattering, for instance, in the example I'm giving. But what's interesting is molecules. And now we have work ongoing within the community that show that you could even identify isotopes using this kind of methods. So how do you search for another Earth? That's the next step in our quest of why TRAPPIST-1 was important and why it was chosen. And for that, we have to understand how we detect planets and how we want to study these atmospheres. And to have the star shining through the atmosphere, you need a transiting configuration, and that limits you somewhat. So if we have a transit, and here I'm placing an example of Jupiter transiting the sun. If we make Jupiter transit the sun, we have the light curve on the bottom of the screen here. So you would have the starlight and the starlight minus the planet and then starlight again. And this deficit of 1% relates to Jupiter being 10 times smaller than the sun. Measuring the atmosphere is a change in this, the depth of this signal here of about order 0.01% for a Jupiter-like planet. And while this precision of 1% is reachable from the ground, 0.01% becomes a bit challenging, and you need usually a spacecraft. Some instruments on the ground have managed to do that. But by and large, you need to know when to observe during the transit, for instance, of the planet and achieve this precision on a large telescope. The issue for finding an Earth became that if you have an Earth transiting the sun, you have a tiny planet passing in front of it, and the transit signal that you see here on the screen has been amplified by a factor 10 because otherwise it was smaller than the pixel. And it means that you need to achieve a precision which is similar to measuring the atmosphere of a planet like Jupiter, but except to do it on a random star, observing whenever, because the Earth will transit, a remote observer seen from the sun will transit for 10 hours once a year. So you need to observe a lot of stars for a long time and not be exactly sure when a transit will happen. And obviously you need to observe several years because the signal needs to repeat to confirm. And so reaching this kind of signal for several years on hundreds of thousands of stars is particularly challenging. This challenge was attempted by the Kepler spacecraft, and it was launched by NASA. It was remarkably successful. You can see here thousands of exoplanets ranked in sizes and orbital period. So it was hugely successful, but its primary mission goal was to measure the occurrence rate of true Earth twins, of planets like the Earth orbiting sun-like stars. And you can see that there is a cruel lack of candidates in this area. And this is not because the mission was badly designed. In fact, the precision of the telescope exceeded expectation. It is just that stars were a little more noisy, a little more buoyant than what we would have anticipated. And there was no way of knowing that before the observations were started. So what do we do? Well, one thing we can do is try to beat down that noise by observing even longer or more precisely. And Plato, which ESA will launch in a few years, will attempt that. But we thought a solution would actually be to simply change the kind of star that you look at. So the depth of transit, this depth here, is the radius of the planet over the radius of the star to the squared power. So if we change our radius of the star here, we actually would increase our depth. And this happens, for instance, like this. So here I just reduced the size of the star by a factor 10. You see the planet now has a bigger contrast ratio, and not just the planet, but its atmosphere as well. And by focusing on the star that is 10 times smaller than the sun, then you can get, again, a 1% signature, which is detectable from the ground and doesn't require a spacecraft. And the advantage, so these are the equations here that rule out the sort of expected signal that you would expect from the atmospheric part of the planet. And this is also in relation to this R star to the squared power. So by changing the star by a factor 10, we've boosted our detection of the planet by a factor 100 and our detection of a potential atmosphere by a factor 100 as well. And once you've decided for a small star, then other advantages fall into place. The habitable zone, so where we would expect liquid water to exist on a planet under 1 bar atmosphere, comes actually closer to the star, which means that you have to less time. For planets around the sun, you have to wait 1 year. For planet around TRAPPIST-1, you can wait only 1 week. So you've gained a speed factor of 50. And then if you're close to the star, so if your planet is close to the star in a habitable zone, then this brings an extra advantage, which is that you need to survey less stars before you get a planet, because the transit configuration is fairly limiting. Only the stars within this triangle will see the planet pass in transit. So you see this star, for instance, let's say you're an observer here, you will see the planet occulting the star. However, if the planet is further and further out, you can see that here you can see the star, unocculted. And very rapidly, this decreases. So by getting closer, we actually need to observe less stars before we have the right configuration to detect a planet. And all those advantages come convoluted with the type of instrumentation that we expect. The James Webb Space Telescope is the next big thing to be launched. Hopefully it will happen in autumn 2021. And the moment we're writing proposals for projects to submit to the telescope. And this telescope will have the right instrumentation to do the transmission spectroscopy of Earth-like planets, including around the sun, except that the mission lifetime is too short for that. This plot here is a summary of what we just looked at. We have the probability of transit here as a function of the mass of the star for a habitable zone planet. And for a habitable zone planet, you can see that these curves uptick the lower the mass of the star is. And this pink box here is the only area where you have enough transits to build up enough signal to make a 5 sigma detections. So let's take Earth around the sun, a habitable planet. If you want to observe it with James Webb, you need 15 transits in order to get a 5 sigma detection, so a reliable detection of atmospheric features. But that means at least 15 years of work. And because sometimes the transits will happen when the star is behind the sun and the telescope can't observe, it really is 20 to 30 years of observations. And yet the telescope will have only a nominal mission lifetime of 6.5 years, will probably be extended. There just are not enough transits within the lifetime mission of James Webb for true Earth analogs. And then we don't have a proper candidate anyway. The pink box is the only area where you have enough transits, and you see it limits to stars that are less than about 15% of the mass of the sun. And that's why we decided to observe such low mass stars. NASA has a spacecraft called TESS. There is a ground-based experiment called MERS that are targeting low-mass stars and trying to find the best targets possible for James Webb. But you see they just skim this pink area. And that's why we decided to build SPECULOOS. SPECULOOS is the search for planets eclipsing ultracool stars. So ultracool stars are these objects, stars and brown dwarfs that are less than about 15% of the mass of the sun. And to realize these telescopes, of which you see here the blueprint, you see behind me, the picture is actually the facility that we now operate. We have telescopes, 4 telescopes at Paranal, 1 in Tenerife, and 1 at San Pedro Martir in Mexico. Those telescopes are there to monitor such ultracool dwarfs. But to realize such a project, we needed a proof of concept. And that's where TRAPPIST and TRAPPIST-1 come into play. TRAPPIST was a small robotic telescope already existing. And with it, we did a practice, a prototype survey. So we first showed our observation on the nearby brown dwarf, showed that we could have detected an Earth-like planet if there had been one on it. Then proposals were sent in order to get funding for the telescopes. And it took time to first assemble the funding, get the call for tender, the construction, and everything. And in the meantime, our prototype survey continued on TRAPPIST until we hit gold rather unexpectedly with TRAPPIST-1. And what started as a small group of friends, a very limited group of researchers, became suddenly a huge international collaboration. There are now dozens of people preparing observing proposals for the James Webb Space Telescope to explore the chemical composition of the atmospheres of TRAPPIST-1 planets. And now the papers that I will describe are mostly on these 3. This is Valérie van Hoetel, who determined the stellar parameters for the planet. There's Elsa van Ducrot here, who has measured the sizes of the planets, and Eric Egel, whose recent paper has nailed down the masses of the planet to incredible precision. So what did the data look like? Well, our detection data is such. You can see here this transit here. So you have 100% of the starlight, and here it drops to 99%. So it's this 1% transit depth that we were talking about. And you see that this is fairly clear. And this is from the ground using a 60 centimeter wide diameter telescope, confirmed by the telescopes in the Himalaya, the Chandra telescope, UCCURRENCE in Hawaii, and the VLT, and TRAPPIST-1c, the second planet, etc. Now, from the ground, we have a limited view of the system. And at some point, we wanted to make sure that there weren't any more planets in the system. So we decided to ask the Spitzer Space Telescope to observe. And we requested 3 continuous weeks of observation, which revealed that the system is extremely rich. And you see here, it is data again. So again, 100% of the stellar flux. Every time it drops to 99, you have an Earth-sized planet passing in front of the star. And here it goes to 2%, as because you simply have 2 planets passing at the same time, and they don't overlap, so they cover twice the area that one would do. And for 3 weeks, we have this light curve. Each of the points here is a measurement by Spitzer. You can see remarkable thing. You can see here a flare from the star. Here is TRAPPIST-1H, and here a second flare. But the transits are mostly extremely unambiguous. And if you collect each of these events together, you can build a picture such as this one, where you have here the transit light curves very well determined. You can see that the depths here are each slightly different, meaning that the planets have slightly different sizes. You can see the duration here are different, meaning this planet goes faster in front of the star than this one, and that's normal. That's Kepler's third law right up there. Those planets are just slower. And we build this image here of a planetary system composed of 7 Earth-like, or at least Earth-sized planets. How do they relate to the solar system? So for that, I mean, this system is very small. You see 6% of an astronomical unit for the outer orbit. So how do you properly compare to the solar system? And we decided to compare it by using the amount of irradiation the planets receive. And that's the plot that you see here. So you see here a planet would receive 5 times the amount of irradiation the Earth does. Here is 1 times the Earth, and here is 10%. Here is the radius of the planet. Here in units of the Earth, again, 1 time the radius of the Earth. You see the Earth is sitting right there. But the TRAPPIST-1 system is remarkably similar to Venus and Earth, and indeed to the entire inner solar system. It ranges from irradiation slightly less than Mercury to slightly more than Ceres. So we have now established those radii. You can see a precision of about 5% of an Earth size on the radii of the planets. Now, how did we determine the masses? Well, something interesting happens in this system. The planets are not in any orbital configuration, while planet C goes twice about the star. Planet B, the innermost, goes exactly 3 times about the star. And this means that you have often conjunction between the planets during which they exchange a bit of angular momentum and orbital energy. And this means that the orbital periods are never exactly the same. On Earth, year after year, we end up almost on the same time. Every now and then we just put a leap second. But by and large, the orbit of the Earth doesn't change. In TRAPPIST-1, the planets are close to one another that the respective gravitational attraction changes the orbital period, and it changes that by a few hours. You see here, if everything was exactly on a metronome, at the very second, all the transits would line up on this line. And you see this one is early and this one is late. And similarly for several of the planets. And we can model this using Newton's equations of motion that we integrate using an n-body integrator. And you see here this transit timing variation, this TTV as a function of time, and you can see that the orbit here has grown by 60 minutes and then has decreased by another 40 minutes. So a peak-to-peak variation of nearly 2 hours over just 300 days. So the orbits keep changing. And you see in gray, these are models, and those models have encoded in them the mass of the planets and their orbital eccentricities, which allow us to measure them. And there, the precision is truly remarkable. As you see here, the planetary masses are known now to 3 to 5% of an Earth mass, which is quite diabolic. You see other measurements reported as other dots here. So here, the masses are always in relation to the stellar mass. So if you increase the mass of the star, you can move the dots up and down. Similar with the radii, they're always in relation to the star. But the transit timing variation is very handy in that we get an absolute measurement of the planetary density. And so those measurements here are not related at all to any external parameters or any assumption. And so we know that the planets have bulk composition that resemble Mercury, Venus, and Earth. This is truly remarkable. The inner 2 planets seem very similar to Earth and Venus. The others seem to be a bit underdense. And so we can build a mass radius diagram like this one, where you have, again, planet radius as a function of planet mass. Earth, Venus, and Mars lie on the 3/4 silicate and 1/4 iron isochrone. And you see here the planets lying slightly above, which means that they're a bit underdense. They likely have more volatile content, maybe more magnesium, carbon, water, maybe thick atmospheres, or maybe they're simply deficient in metals like iron. So we will see. Now, certainly we have enough evidence that we need to investigate those atmospheres, and we will do so in the coming years, thanks to James Webb. So is TRAPPIST-1 special? And how often do you find such configuration? That's what we're trying to understand with SPECULOOS nowadays, and we don't yet have a detection. However, we can place some constraints by looking at what other type of stars were detected, how many planets were detected around, how many stars were surveyed, and how many planets were detected around them. And if you take the initial prototype survey, we had 50 stars and 1 detection. The Kepler spacecraft that NASA had 107 stars with similar to TRAPPIST-1 in color, and had 2 detections. It implies an occurrence rate of 30 to 45% of these low mass stars having systems with periods, planets within 6 days around the star. The nearest star to the solar system is Proxima Centauri, and it has an Earth mass planet orbiting it. It was found with radial velocity. It's also less than 15% of the mass of the Sun. And the probability that it would transit, the geometric probability, is 1.5%, meaning that you need to survey 66 stars before you would find Proxima B in transit if all of those stars have a habitable planet. And in fact, within the volume that TRAPPIST-1 is, it implies that the occurrence rate is it's consistent at the moment with 80% of those low mass stars having such a habitable planet, which is incredibly large, like so large that it becomes unbelievable in a way. But it shows that those stars likely host many, many such planets. And so if we go back to this diagram where the majority of stars are at the bottom of the main sequence, you have more than 3 times more stars here than Sun-like stars. Less of them are binaries, by the way. And we have, it looks at least 3 times more rocky habitable zone planets around these stars. And it means that there could be 10 times more Earth-like planets orbiting such low mass stars than single sun-like stars, bringing an interesting argument into the anthropocentric view of life in the universe. So I'll start finishing my talk here. So the advantages here that you have of TRAPPIST-1 is that its configuration makes it optimal for atmospheric characterization. You have, and that's because of the small size of the star, which makes it more amenable for the atmosphere to be visible. The comparisons are also possible between 7 worlds, and I don't know if you noticed, but they were almost spread linearly in log space, almost like a perfect theorist dream, where one planet has receives 4 times as much light as the Earth does, and the next twice, and then Earth has once, and exactly by factors of 2 each. So we can compare between them, and that's very helpful, particularly in the search for biomarkers. The presence of oxygen, for instance, on Earth is very noticeable when we look at the atmospheric content of Venus and Mars. And so having 7 planets to compare is handy for that. It's a chance to study habitability in non-strictly Earth-like conditions. So we expect the planets to be quite different, notably to be synchronized to the star, so to show a permanent day and a permanent night side. And I think the main milestone of TRAPPIST-1 is that it may show us the most common mode of planet formation, far more common than the formation of planets within the solar system or the formation of the Earth. So how much time do I have, Emma?
You have about a minute or so left.
All right, let me then go to some of my final slides. So I will just say that TRAPPIST only observed 50 systems now. SPECULOOS, North and South, are monitoring 1,000 systems. And we hope that in the next, well, I wrote 5 years, but within the next 2 or 3 years, we will discover tens of new planets. And then will become the work of starting to explore those atmospheres. And here, I'm calling on your imagination. In the solar system, we know of only 3 Earth-like planet atmospheres. We have Venus, we have Earth, and we have Titan. And those couldn't be more different from one another. They're extremely different. Now imagine if we have 20 to 30 new planets that we can explore. What will we discover? Will it be, like a spectrum between the 3 that we know of? Or will it be ranks of 3 or maybe 5 classes? It's really left to our imagination at this time, but hopefully we'll find those planets, observe them with James Webb, and then start the search for life. So I'll thank you for your attention and now call you for questions. Thanks.
Amaury, thank you so much. That was an absolutely wonderful presentation. So yes, let's open for questions. Over to you, Shona.
Yeah, thanks, Amaury. That was really, really interesting. So we've got quite a few questions. So we'll just see how many we can get through. So the first one comes from Amy Grigorescu, which I hope I pronounced correctly. And she was wondering whether any of the TRAPPIST-1 system's planets are tidally locked.
Yes, indeed. We think so. This is what we expect from theory. By tidally locked, we mean the same way that the moon always shows the same face to the Earth. So the planets are expected to show the same face to the star, have a permanent day and permanent night, which would affect the climate. However, until recently, it was hard to know of any way we could measure whether this was true or not. But thanks to a collaboration with Emmeline Beaumont, a professor at the University of Geneva, she actually discovered that, or noticed that, because of the subtle motion of the planets and the interactions between one another, that it encodes the rotation of the star as well. And if the planets rotate ever so slightly off from a tidal synchronized state, as low as 1%, we will see a deviation on the time of the transits of order a few tens of 20 seconds in the next few years. So we might actually be able to measure the rotation rate, or at least place an upper limit on the rotation rate of this planet above tidal synchronization. So far as it looks like they're pretty synchronized.
Oh, that's pretty cool. Okay. The next question is from Paul W., who asks, in terms of habitability, SETI, and round trip times, have we done long surveys of every star within 40 to 50 light years?
not every star. That's why we have our survey. Actually, our survey is looking at these low mass stars within 40 parsecs only, so we are quite limited. And that was mainly because we needed the equipment. I'm not sure I understood what about round trip, the round trip part of the question. Could you repeat, please, Shona?
Yep, he says, in terms of habitability, SETI, and round trip times, have we done long surveys of every star within 40 to 50 light years?
Yeah.
He also then says, Kepler surveyed very distant areas, so we will never do a round trip exchange of radio with those systems.
Oh, I see.
Yeah.
Okay. Yeah. So no, we haven't finished this survey, but so I don't know the SETI efforts, but certainly in terms of exploration for planets, we haven't. One thing to remember is that once we have, like for most of the systems, we don't detect transiting planets. But it doesn't mean planets are not there. Most of the planets don't show. Most of the systems don't transit, and so after we've done our survey, I think there will need to be more work to establish the presence of planets using other methods like radio velocities on some of these ultracool dwarfs. I expect most stars to have a planetary system.
Okay, we've got one from Paul Murden, and he asks, do the planets exhibit a Bode's law?
Yes, it keeps coming back. So there is maybe something of that kind. Like it's a bit controversial to talk about it, but it seems that some systems are arranged, and one can understand it in such a way that each planet has a Hill sphere, so a radius around which they will dominate the local gravitational field. And then those Hill spheres usually don't overlap, otherwise the system would be unstable. Because of that, it creates a fairly natural parallel. If you pack planets, the Hill sphere is related to the radius, to like the semi-major axis, to a power. I can't remember exactly which actually. And so it would naturally lead to a parallel. However, planetary systems do become unstable, and we see several systems. And a thought is that the systems are born with fairly packed systems. And then as time goes by, linearly with a log of time, actually, you start losing planets through gravitational interactions, collision, and expulsion. In TRAPPIST-1, it didn't happen, but in other systems, it probably did, which would leave holes and made the Bode's law sort of incomplete. There would be missing integers, so to speak.
Okay, we've had a lot of questions actually. So what I'm going to do is I'll pass them on to Amaury, of course, but in the interest of time, I'm going to hand you back to Emma because I think we need to move on to our next speaker.
Okay, thank you very much, Shona. Yes, so I think Amaury will try and answer some of the questions as we're going along. Okay, so thank you so much again for that wonderful talk. And I'm going to introduce our next speaker now, who is Josh Nall from the Whipple Museum of the History of Science, Cambridge University, to give the RAS Diary talk on Calculation and Conflict, Anniversary Reflections on the Early History of the RAS. Over to you, Josh. Thank you.
Thank you, Emma. I presume you can hear and see me. And can you see my slides?
Yes.
Excellent. Okay, fantastic. Brilliant. Well, thank you very much for having me. I'm very pleased that we can continue this tradition of the diary talk. And obviously, this year was the 1 year where choosing which anniversary we would celebrate with our diary talk was a very easy job. So I'm going to be presenting here a talk that I originally prepared, a much longer version, or to present at the AAS meeting in Hawaii in January. So before I get going, just a quick thank you to Lindsay Fletcher for the invite, and to Siobhan and Richard, Louise, Emma and Shona for facilitating all of this. So the obvious place to start my talk is here at the very first meeting of the Society on a bitterly cold night. It was 11 degrees below freezing. And we have here a very modest description from John Herschel's diary of him dining at the Freemasons Tavern to meet Dr. Pearson and other gentlemen to consider of forming an astronomical society, early January 1820. And that was a meeting ultimately of 14 men aged in their 20s to their 60s. And my task this evening is simply to explain why these 14 men met to form such a society at that point. And so what I want to do is I want to resist the temptation to think that, well, just forming societies was a typical act of the age. And rather, I want to explore the specific agenda of those founding members. So this is a list of the charter members of what was then called the London Astronomical Society. It's a select group, and hopefully there are some recognizable names here. I say recognizable not least because I hope you have all been reading and enjoying Mike Edmonds' wonderful series in ANG over the last couple of years, where he's given biographical accounts of all of these men. Their basic composition is listed here: 3 stockbrokers, 3 gentlemen of independent means, 2 schoolmasters, 2 military men, a retired merchant, an administrator retired from India, a lawyer, and somewhat anomalously a 24-year-old visiting from Poland. What can we learn from this composition? Well, a few things are worth pointing out off of the bat. These are, by and large, not men of the aristocracy. They are not high, grand amateurs of wealthy backgrounds. They are mostly from the mercantile upper middle class. But also, off the bat, I want to stress who is not amongst this group. And some of the people absent from this group will reveal some of the founding agendas in play here. There are no women in this group, perhaps not surprising for the age, but this was very much a gentleman's club and a practitioner's club. It was not interested in widening access to astronomical knowledge. Consequently, there were also no popular lecturers. We should remember that aside from the Astronomer Royal and his cohort of assistants in Greenwich, most of the people making money from astronomy in this period were popular lectures. There was a very popular series of astronomical lectures during the Lent season, when fictional theatre was banned across the capital. But no popular lectures were invited. No instrument makers were invited. This again might seem unsurprising to us, but we should remember the scholarship of Jim Bennett has reminded us that during the 18th century, many of the preeminent makers, men such as Graham, Ramsden, Troughton, Short, Dolland, Nairn, were fellows of the Royal Society and were very much active contributing partners to the astronomical enterprise and saw themselves as such, but they were not, the next generation of instrument makers was not invited here. Perhaps most strikingly though, and really the most revealing absences are that the Astronomer Royal, John Pond, was not invited, and the President of the Royal Society, Joseph Banks, were not invited. And these absences in particular were deliberate, I want to argue, and they reveal a particular ideology of the Astronomical Society's founding members. Now, I borrow from my colleague William Ashworth the title of business astronomers to describe this group. Under this umbrella term, William Ashworth has identified in the founders of the Astronomical Society a shared set of ideals and methods that he, I think very persuasively, has linked to larger interests in the world of Cambridge mathematics and the City of London. Most of these men were men of business themselves rather than dilettante aristocrats, and they shared a joint commitment to a particular future for their discipline of astronomy, built on the same ideological commitments that drove their mercantile successes. So a sense of this ideology can be gleaned from the Society's founding address, written by John Herschel and Francis Bailey and circulated ahead of the first public meeting. And this is what here they wrote. One of the extracts from this: beyond the limits of our own system, all at present is obscurity. Some vast and general views of the construction of the heavens and the laws which may regulate the formation of motions of sidereal systems have, it is true, been struck out. But like the theories of the earth, which have so long occupied the speculations of geologists, they remain to be supported or refuted by the slow accumulation of a mass of facts. And it is here, as in geology, that the advantages of associated labor will appear more eminently conspicuous. So here I want to argue we see the first inklings of what will become an abiding concern for the Society. On the one hand, an obsession with the accumulation and reduction of astronomical data, and on the other hand, a skepticism of cosmological speculation. To understand the origins of this ideology, an interesting place to begin is actually by thinking about the first president of the society. And the first president of the society was actually this man, not William Herschel. Edward Adolphus Seymour, the 11th Duke of Somerset, was offered and accepted the first presidency of the society, and then almost immediately retracted that acceptance. This is a letter that he sent in early March to the society, retracting his acceptance of the first presidency. I should say that Seymour was a noted mathematician, and therefore that was kind of one of the reasons that he had been mooted as a suitable president. And we see in this letter the reason that he retracted his acceptance. The great names which are to be found in the list of your members have given ample grounds for trusting that as nothing was intended inimical, so nothing could follow prejudicial to the interests of an old, respectable and chartered body. Its president is, however, of quite a different opinion and apprehends the ruin of the Royal Society. To Sir Joseph Banks I have been long and strongly attached, not only by the ties of public regard, but those of private friendship, and my remaining in post, which he considered as a hostile position, might be liable to unfavourable comments and would certainly be very painful to my own feelings. So it is the president of the Royal Society who has scotched this appointment, and that is because the president of the Royal Society, Joseph Banks, is vehemently opposed to the establishment of an astronomical society. What's important to understand here is that this antipathy ran both ways. The business astronomers detested this man, Joseph Banks, every bit as much as Banks loathed the upstart new society. Indeed, my argument here is very much that the Astronomical Society of London was born out of a frustration at the state of their science and forged in opposition to what they viewed as an entrenched and corrupt authority figure at the highest levels of British science. And this opposition, this entrenched and corrupt body of British science was embodied above all by this man, Joseph Banks, an aristocrat, dilettante, botanist and clubman who by 1820 had been president of the Royal Society for more than 40 years. And his distaste for the exact sciences was well known, and his management of the Royal Society was notorious for its granting of insider privileges and backroom handouts. And it is striking to the degree to which the business astronomers did not play by these aristocratic rules. One of the most famous examples is one of our founder members, Charles Babbage, who is now famous. One of the things he's very famous for is publishing this book in 1830, his bombshell Reflections on the Decline of Science in England and Some of Its Causes. And this was a book that laid bare for all to read the jobbery and mismanagement at the heart of scientific London. It was a vicious broadside against the Royal Society. And this is how Babbage put it to a friend, Dawson Turner. The power Banks possessed was not that which is yielded to high moral character, but was almost solely given to his great wealth. The subservience and sycophancy which characterized the Royal Society during his long mismanagement of it has brought it to its present position. So to the business astronomers, the charter members of the Astronomical Society, Banks represented everything that was bad and rotten about the state of British science. These can be characterized as a form of science that was aristocratic, monopolistic, undemocratic, secretive, based on a system of patronage, and hostile to the mathematical sciences. And William Ashworth's point is that the business astronomers founded the Astronomical Society of London to steer astronomy in a different direction, built on sound methods of mercantile capitalism. And this is just a pull quote I've taken from his wonderful paper, The Calculating Eye. Quote, "The business astronomers set out to develop a trustworthy approach to the accumulation of intellectual and financial capital through the establishment of a firm calculating base in which data were constantly monitored and reduced." Now, obviously, behind this political commitment to opposing Banks and the Banksian empire was also a scientific commitment to a particular model for the future of astronomical practice. And that model was not, it must be recognized, sui generis. We have a characteristic description of that model for the future of astronomy here in Herschel's very successful preliminary discourse on the study of natural philosophy. He argued that a correct enumeration and description of the fixed stars in catalogues and an exact knowledge of their position supply the only effectual means we can have of ascertaining what changes they are liable to and what motions too slow to deprive them of their usual epithet fixed, yet sufficient to produce a sensible change in the lapse of ages, may exist among them. Such a model, based on a comprehensive collective assessment of the proper motions of the stars and on the locations and nature of double stars, which of course Herschel and South had worked on a great deal in this area. These practices essentially relied upon the marriage of massive data collection and rigorous mathematical analysis. The problem, as the business astronomers saw it, was that in Britain at least, suitable stellar catalogues were thoroughly lacking. Data languished unreduced, and that which had been reduced tended to have been done poorly, or at least not in a consistent fashion. And the solution to this problem for the business astronomers lay by casting one's gaze to continental Europe. Most of the business astronomers were young, they were modernizers, many of them had come up through the Cambridge mathematics tripos, and one of their abiding interests was in mathematical reform along the lines of continental European mathematics. This was at a point where Cambridge was still teaching Newtonian fluxion notation instead of Leibnizian notation, and the business astronomers were very keen to push reform. And so they took as their model some of the work that was being done on continental Europe, particularly in astronomy. Their model was this man, Friedrich Bessel. And Friedrich Bessel, by deploying just these modish continental mathematical theories that the business astronomers so admired, was among the first astronomers to establish astronomical constants capable of sustaining a uniform system of reduction that could correct for aberration, nutation, and refraction. And so we have this wonderful quote that John Herschel gave in an address to the Astronomical Society in 1829, where he describes Bessel's work as the perfection of astronomical bookkeeping. And so it was the incorporation of this Besselian paradigm of systematic collective astronomical data reduction that the early members of society very assiduously pursued. And I can fall back here on the magisterial 1923 History of the Royal Astronomical Society written by H.H. Turner. I'm sure you've all got a copy on your bookshelf. And this is what Turner himself says about these founding members. We find ample evidence in the history of the early years of the new society that its prime motive was precise measurement and systematic calculation. It might have been supposed that the more picturesque work of its first actual president, Sir William Herschel, would inspire the active members to follow him in examining nebulae, stellar clusters, and other objects of special interest. Instead of this, Francis Bailey led them on a campaign of meridian observation, star corrections, and improvements of the Nautical Almanac. And it's here in this final phrase of Turner's, this improvement of the Nautical Almanac, that we find one of the most important concrete results of the business astronomers' founding ideology. One of the first great achievements of the business astronomers after establishing the society was a full frontal assault on the Nautical Almanac and the Board of Longitude, the body that was governing the Nautical Almanac. As I'm sure, I hope many of you know, this book had first been produced under Neville Maskelyne in 1767 and had been published annually out of Greenwich, an essential aid to navigation at sea, finding longitude by lunar distance method. And the problem, as the business astronomers saw it, was that the Nautical Almanac, after Maskelyne's death, had fallen into a state of decay, which is to say, under the guidance then of John Pond. Hence, he was not invited to the first meeting because they wanted to actually reform the almanac and take it out of control of Pond and the Board of Longitude. And because one of the approaches of the business astronomers was to wage their battles completely openly, they were very against this aristocratic approach of doing things anonymously or behind closed doors. What they did was they published pamphlets and they signed them. So Francis Bailey in 1822 publishes a pamphlet with his name on it entitled Remarks on the Present Defective State of the Nautical Almanac. So this was completely out in the open. And in this pamphlet, Bailey very viciously attacks the present state of the almanac. He says it's begun to lose its character for accuracy and had now become a byword among the literati of Europe. And one of the people that he was very seriously attacking at this point was the superintendent of the almanac, Thomas Young. He was secretary of the Board of Longitude, and this was his private plea to the Admiralty that he was under attack. He wrote, "Mr. Bailey will never rest satisfied until the Astronomical Society, not content with the humiliation of the Royal Society, shall succeed in dictating to the Admiralty and the British Parliament and the House of Commons." The coda to this story is that this campaign was an extraordinary success. The attack by the Astronomical Society on the almanac led to a parliamentary inquiry. In 1828, the Board of Longitude was abolished. And ultimately, after the Astronomical Society was asked to form a committee to review the Nautical Almanac, its control was passed into the hands of the business astronomers. Obviously, ultimately that control, the real power and control, was wrested when one of the great business astronomers, George Biddle Airy, was appointed as Astronomer Royal in 1835. So the reform of the Almanac and the ascendancy of Airy to Astronomer Royal were really the crowning achievements of the early years of the society. So before I leave you, I want to kind of characterize some of the more lasting consequences of this ascendancy of the business astronomers in the early years of the society. The first of these that I think is very striking, which is very evident under the reign of Airy at Greenwich, is that the business astronomers and through the society push the promotion of mathematical theory over observational astronomy. We have this striking quote here from George Airy to his friend Harcourt. "The work of a mere observer is the most completely horse-in-a-mill work that can be conceived. The beau ideal of an observer of the highest class is a compound of a watchmaker and a banker's clerk. Most of the observers that I know are far below this standard. You will see, therefore, that the mere observer is a person very, very far below the mere chemical experimentalist." And obviously, this diminution of observation was very much pushed such that what was promoted was the post-observation application of mathematical theory to the data that is produced by the observer. So the observer becomes really a drudge worker in the Airy model. And this is when you start to see things like the personal equation developed at Greenwich Observatory and other observatories to try and completely turn the observer into almost a kind of mechanical automaton. With this promotion of theory also comes the diminution of the status of instrument makers. I mentioned that in the 18th century, instrument makers had risen to very senior positions within the astronomical community. We see, and Jim Bennett has written about this, we see in the first half of the 19th century a diminution of the status of the instrument maker. And we see here a quote from Benjamin Gompertz at an early meeting of the London Astronomical Society, explaining why instrument makers were actually not that important. It's because instruments supply data to the theory, but it is the theory which invents the instruments. It is theory which points out the cause of the defects, theory which directs the practitioner to the requisite improvements. And so with this promotion of mathematical theory finally came a general repudiation of the more picturesque approaches to astronomy, the kinds of approaches that had been characterized by William Herschel, these approaches which promoted discovery and speculation and cosmological theorizing. So for example, Airy wrote to his friend William Whewell in 1857 that he could abandon such showy things as discovering comets and planets and can therefore do the dull meridian work surprisingly well. And this is known to and approved by the astronomical public of England, but it would not do in France. And so Airy would credit the success of that approach, that dull meridian work approach, to the success of the Astronomical Society in promoting the ideals of business astronomy. Now, I don't have time here to give you the next part of the story, so I will leave you just to say that what I should note is that these changes that the early members of the society brought in were neither universal nor permanent. And if I have more time, I would go on to discuss challenges to this ideology of the business astronomers, both during the years of ascendancy, but most strikingly, the challenges that emerge in the new era of astrophysics that emerge only a few years after this quote. From 1859, the work of Bunsen and Kirchhoff inaugurates a completely new era of astronomical research. And it's really with the advent of astrophysics that you start to see striking challenges to the work of business astronomers. But if you want to read more about that, you can read the first chapter of my book, which is called News from Mars, where I account in great detail. But I should finish and wrap up now, so we've got time for questions. Thank you.
Josh, thank you so much. That was absolutely fascinating, really enlightening talk. So thank you very much for giving that presentation. Okay, we do have some questions. So over to Shona.
Yeah, thanks, Joshua. This mere observer found that really interesting.
I thought that might upset some of the members of our audience. I don't know.
Mildly offended, but so there's a few questions. So the first one is from Nick Canas, and he asks, what was the status of John Flamsteed's catalogue by the time of the founding of the RAS? From John Herschel's quote, it would appear that it was not seen as being especially accurate.
Yeah, that's a good question. I suspect not. I mean, I think the early members, they gave due deference to their predecessors. Obviously, Flamsteed's catalogue would have been considered near the top of the tree simply because it had been produced from Greenwich. And so it was one of the most complete and usable catalogues. They were particularly frustrated at the propensity for observatories to not publish and to not reduce data, and at least Flamsteed's catalogue was reduced at Greenwich. But I think that there was a recognition that the advances in continental mathematical theory, particularly the work of Bessel, combined with developments in instrument making, meant that it would be possible and should be possible to produce much more accurate and extensive catalogues. And so that was really their push. But they certainly, I don't think they would have said anything rude about Flamsteed.
Well, okay, so there's also a question from Rob Peeling, and he asks, the criticism about the Nautical Almanac is interesting. H. Turner recounts James South reporting that the marine cartographer W.H. Smythe preferred to trust the French almanac and gave his UK version away to a foreign commander. Is there any evidence of other agreement from naval commander of the problem, Beaufort perhaps?
Yeah, no, I mean, there's a wonderful anecdote associated with that. What South actually reports is that Smythe gave the British almanac to a Spanish captain as a courtesy while he was sailing in the Mediterranean, because the Spanish captain had given him a European ephemeris. And the way South ends the anecdote is he says that Smythe made it back to Britain safely, but there's a rumor abounding that the Spanish captain was never seen again. And he publishes this. This is on the record. So he implies, it may be a joke, but he implies that ships were being sunk because the British Almanac was so bad. So certainly whether I can't, that's a very good question as to whether there are naval men complaining about the Almanac at this point. That I can't answer. And in fact, that is something that I should look into, because it would be very interesting to see if there are actually people coming back from voyages complaining, throwing their Almanac down on the table in Greenwich and saying, this is useless. But I can't think of anything off the top of my head to that extent.
Okay, so I've got a question from Steve Miller, and he says, did anything change in relations between the Astronomical Society and the Royal Society when Davy took over from Banks and started to move the gentlemen, in inverted commas, members out of the RS?
Yes, I think so, but I think it was reasonably slow. I mean, Davy had a hell of a time as president of the Royal Society. He joined it it was in a pretty parlous state because of the Banksian approach, which had loaded the membership with aristocrats and clubmen who had no interest in science. And I think Davy found it a bit of a nightmare, frankly, and had a bit of a miserable time. And he tried very hard to move it back towards being a serious society. But of course, over that period, between the time of Banks dies later in 1820. Banks dies in May 1820. By that point, and by the time Davy's trying to turn it around in the 1830s, a lot of specialist societies had been established. And it was recognized that one of the reasons that the Geological Society had been established, the Chemical Society, the Astronomical Society, this story was not unique to the Astronomical Society. Lots of specialist societies had been established because the Royal Society had been such a useless space. And I think it takes a lot longer than Davy, frankly, to steer the ship back. It's a much longer story to get the Royal Society back to respectability. Davy starts that journey, but it takes a long time. I mean, as you saw, Babbage's book comes out in 1830. The quote I gave you is 1835. So by the time Davy's in charge of the society, it's still being talked of as completely awful in the views of these younger, modish, business-minded scientists.
Thanks. I'm going to pass you back to Emma. We have a few more questions that I'll pass on to you afterwards. But yeah, that was super interesting.
Thank you very much, Shona, for helping with the questions, and thanks again to the speakers for today's meeting, both wonderful presentations. So all that remains is for me to give notice that the next monthly A&G open meeting of the Society will be on Friday, the 11th of December. So thank you all for joining us, and we hope to see you all very soon.